Hello, I'm Sihang from the University of Virginia. This is our lightning talk for PMFuzz, test case generation for persistent memory programs. I like to start with the benefits from using persistent memory. Persistent memory features high performance, digestibility, and data persistence. It allows programs to bypass OS interactions such as file systems. But the program then needs to ensure the correct consistency of persistent data. In other words, it needs to recover to a consistent state after failure. So, direct access to persistent memory benefits performance, but makes it harder for programming. Our private works, PMTest, and XDetector are testing tools for detecting bugs that break the correct consistency guarantee. But there's a prerequisite. The buggy program path needs to be executed in order for the bug to be detected. Here's an example from B-tree map. After removing an item, it checks the number of items and then perform rebalancing if it's less than some threshold and may later perform rotation. The left side is a common path because it is hard to satisfy the if condition. But what if you have a bug in the less common path? We need to satisfy both conditions by using a strong test case, so that program paths are not always trivial. Therefore, the goal of this work is to design and implement test case generator for better coverage in testing persistent memory programs. And the immediate question is, can we use any existing techniques? Fuzzing is a commonly used test case generation technique. Here is the procedure. First, we have a set of initial test cases. The fuzzer first mutates the test cases and executes them on the program. The fuzzer keeps track of the statistics such as pass coverage during execution. Test cases that contribute to better coverage will be saved and mutated again. There are two key aspects. First, what is the input that needs to be generated by the fuzzer? And second, what is a good coverage metric? We also need to answer both questions when fuzzing persistent memory programs. Now let's take a look at the first aspect, input generation. A persistent memory program first takes an empty image, executes some commands, and produces a new PM image. Later it executes more commands and encounters a failure, so it ends up with a crash image. From this procedure we can tell there are two types of inputs. The first is the input command, and second is the PM image. The PM images can be both normal images and crash images. Therefore, the fuzzer needs to mutate both commands and images. Conventional fuzzers are good at generating small inputs, but not good at generating large inputs like a PM image. There have been works that generate images for file systems, such as the ext3 file system. Given the layout, it is possible to precisely perform mutation at some of the entries. But PM images do not follow a standard layout. For example, B-tree and hash table have very different layouts. So, how can we mutate PM images with customized layouts? We find that the output image of the program is always a valid image. For example, the hash table after executing some commands, we have some keys mutated, which is a valid image. And after executing some more commands and encountered a failure, we have another valid image of a crash image. So our key idea is to use the program logic for mutation. The second aspect is coverage metric. We know that crash consistency concerns about PM accesses that maintain the persistent state. Here is a control flow graph with PM accesses labeled. If we use a conventional fuzzer, it will treat all the paths with the same priority, but only one of them covers PM accesses. A good coverage metric should be focused on PM accesses. Therefore, conventional fuzzers do not focus on crash consistency, which is what we mostly care about. Here is our key idea to achieve better coverage. We introduce another type of path, PM path, a program path that contains PM accesses. By performing targeted fuzzing on PM path, we can achieve better efficiency. Putting those key ideas together, we have our tool, PMFuzz. It is a test case generator tailored for PM programs. It generates commands and PM images for better PM path coverage. First, as the program is compiled and executed, during execution, PMFuzz tracks the PM path coverage and select good test cases that achieve good coverage for testing tool, and finally provide a bug report. Finally, I'd like to summarize this work. Programming for persistent memory systems is hard and error-prone. It is critical to have strong test cases for better bug coverage. PMFuzz is a test case generator tailored for persistent memory programs. Test case generated by PMFuzz can detect 12 new bugs using our existing work, XDetector, and these new bugs cannot be easily detected with simple test cases. The artifact is available in the following link.